There's lots of seats on the floor if anyone wants to. This is where the slam dancing happens. Okay, well, good morning. And welcome, everybody. These little tread things called continuous track, I don't know if you saw them just outside here digging around. There's at least two of them. One has got a garbage pail and the other guy's just digging, but we're going to talk about that today. So with the sort of, I hope what it is you're getting the feeling here is that physics is supposed to be about real stuff. And we're trying to describe the real world, and sometimes it does get a little philosophical. I've had philosophy arguments with some of you. But the basic goal here is to understand the world around us and how stuff is working. So we're going to get into some examples, rolling without slipping. There's a cool video of some slipping without rolling, which Jonathan made, I'm going to show you. On Friday, PhysU has set up, I still have to get someone to open the doors for them, a study session that is going to, so it's in room 122, which is one of the practicals rooms, and they're going to set up snacks in the 125 area. And there'll be various second, third, fourth year physics students there to try to help you out. Nobel Prize was announced the other day. So they demonstrated this is an experimental Nobel Prize, extremely short pulses of light, attosecond pulses, which can be used to measure rapid processes in which electrons can move or change energy. So looking at how electrons move. I mean, this is what life is all about, right? You've got outer electrons in your hand, okay? If you touch someone, then I guess your outer electrons are repelling the outer electrons of your friend, right? You know, this is again what physics is really about. So what's a Nobel Prize? Well, it's $11 million. Well, 11 million Swedish krona, which turns out to be about $1 million, and they have to split it between the three of them. But you get also, if you go to Berkeley, they have NL parking spots, which are for Nobel laureates. Okay. So you can get free snobby in California. I used to live there for 6 years. Parking spots are a big deal because everyone lives in their car in California. Bizarrely, because the weather is nice, so why would you not bike? I used to bike, and it was really funny. I used to bike all the time to work when I was living in California, and one day I had some boxes to deliver or something, so I drove my car in, and people were going, "Oh, congratulations, you got your license back." And it turns out the rumor was with everyone that I had lost my license for drunk driving or something, because that's the only reason anyone in California ever rides a bike. So, I like riding my bike. Okay. There is the pre-course survey has now been scanned in. Remember what that was? Way back in week 0 of practicals, you wrote those, I think it was 78 multiple choice questions. So it's worth 1 point, it's like a 12th of a practical. Practical is worth 12 points. Do we have a class on Thanksgiving Day? So the university is closed on Monday, October 9th. It's called Canadian Thanksgiving. It's just like American Thanksgiving, except it's just way earlier. I don't know. Well, except in maybe not quite as big of a deal. And also, there won't be any practicals next week as well. I have found it's just way too confusing when the Monday gets all out of whack with everything, and plus it's Tuesday's test, right? So, so there's that. So we'll do that, and then I will have class back here on Wednesday and Friday next week. So it sort of throws you off a bit, but that's what's going on. For you? Yep. Yeah, you got to come here Tuesday evenings. You got to keep your schedules open for that. It's only 3 Tuesday evenings this semester, but October 10th is one, and I think there's another November one that comes up. Some questions about the problem set. Is it okay, if you want to write on a tablet, I guess, and upload that image? You need an image of you writing out a solution for the problem sets due on Sunday. Okay? I don't care if it's. I would just write it on a piece of paper and photograph it. Send in the JPEG. If you do take a photograph, try to set your iPhone to most compatible images so you're saving a JPEG and not one of these high efficiency images that are hard to open. with anything other than an iPhone. So. And then just a question, do we have to use this F, E on O? I would say you can use whatever symbols that you want, but there is a reason why she uses all these E, 1 on 2, is that if you're doing like a force diagram of object 2 or something, you want all the forces to be on 2, because it's easy to accidentally put forces that are not acting on that object. So the E on O subscript, I think, is a good habit to have, so you can check that all your force diagram forces are acting on that object. What else do we have? How can I keep awake during classes? And there's this, I don't know how people use ASCII, but before the class I am with big eyes, and right after the class starts I am bzz. So I don't know. I mean, I would recommend you could take notes, meaning like get a notebook and actually write out notes. I used to do this, and I would write out anything that was on my mind, and I ended up doodling or I would write notes to my friends, that kind of thing. So it's a good way. I find that physically writing stuff out helps it kind of connect things to my mind. Such a suggestion. Okay, sorry for the impending morbid physics joke. What is the cheapest way to die? Free fall. Pretty bad. And then of course also Ida Conlu, happy birthday. So. Okay, let's do this one. This is a question that I had hoped to ask last time. A tennis ball is launched at an angle, so should we do it? A is just after it leaves my hand, B is top of its flight, and C is kind of when it reaches that same height but on the other side. At point B, top of that path, which of these 5 statements is true? Thank you. I was aiming for those coffee cups, but... So if you think you know it from this list, please pair up and share your answer. So this is all during the flight, like before it hits any other objects. Okay. Survey says... There's a drum roll. Velocity is horizontal and the speed is minimum, which I like. It's not 0 actually. So the way it sort of looks on this diagram is that if this is v0, the initial velocity that it was at just after it left my hand, and there's some launch angle of that velocity vector relative to the horizontal, then you would say that v0 in the x direction, I guess, if you define x to be towards the right and y to be up, is equal to, I think it's going to be v0 times cosine of theta. So you have to kind of remember your whole right angle triangle. There's your theta. That's v0x, and this is v0y. And that's your v0. Your actual velocity is always on the hypotenuse, and then you break it up into what are the components. And so sine of theta is the opposite over the hypotenuse, and you rearrange that, you get v0y. And then this, by the way, is a constant. If you neglect air resistance, then Vx equals V0 x, okay, which is just always to V0 cosine theta. So it never goes to 0. Nothing goes to 0. So I guess the speed at any point, right, speed is V is just equal to the square root of Vx squared plus Vy squared. So as Vy decreases and goes to 0 at the top of the path, I guess the speed will be minimum. And then it actually starts speeding up again as it comes back down. And that was the idea. During projectile motion, this is the second question this morning's quiz, in which projectile was launched at some angle above the horizontal that's less than 90 degrees, so not straight up. At which of the following positions does the projectile have 0 speed? Well, it never has 0 speed unless it was launched straight up. And so someone put on the pre-class survey, I remember covering this in class, you mentioned that the velocity is momentarily 0 at its highest point. Well, that is if I toss the ball straight exactly up. And then in that case, the horizontal component of the velocity is 0, and it's always 0. So it's kind of tricky. Also on this morning's quiz, there was, let's see, the vertical is a question of which of the accelerations below has the least magnitude. Supposed to be V. The vertical component of the projectile's acceleration at its highest point in altitude. So I think the vertical component of the acceleration is just 9.8 meters per second squared. Well, it's down, maybe negative. The projectile's acceleration during the application of the force that launches it from rest. So this could be, I would say, pretty high. Okay? If you're just as I'm actually throwing the ball, I'm probably accelerating it quite a lot, I would think. Horizontal component of the projectile's acceleration, so this is 0. Horizontal component of the acceleration, if there's no air resistance, is just always 0. A sub x is 0. Projectile's acceleration at its highest point in altitude, again, that's going to be 9.8 meters per second squared. Projectile's acceleration right after it changes direction after reaching its highest point in altitude. Again, that's the same. So most of these are just the same. As it's traveling, it's just got this 9.8 down the whole time. Except when it's being thrown, I would think that's going to be non-zero and pretty high, I guess. So I wanted to do this example. What is the angle you should throw a ball so that it travels the longest horizontal distance? This is range, I guess, assuming you throw it with the same initial speed. And then there's this trig identity that sine of 2 theta equals 2 times sine theta times cos theta. So I'm going to assume, I guess, as usual, no air resistance. And I'm going to kind of draw it. So I've got a flat surface. It's launched with some v initial. So it's going to have v0y, there's your theta, v0x. And then it's going to go like that and fall down again. And I can set x is this way, y is this way. The y final equals y initial. We'll call that 0. Because it falls down to the same place it started at. And from there, your v0x is v0 cosine theta. That's just your vx. It's always constant. And v0y is v0 sine theta. So we can use the y component first. And we can say that a sub y is negative g, where g is a positive number, it's 9.8. And we'll use y is y sub 0 plus v0y times t plus 1/2 a sub y t squared. That's one of the equations of constant acceleration from back in chapter 2. Can't remember which one. And some of these are 0. The final is the initial. And then you're going to add plus v0yt and then minus 1/2 gt squared. Now I'll just solve for t, I guess. So I think what you get is you get v0 y t equals 1/2 gt squared. I think if t is not 0, then you can divide both sides by t. So I can cross off this and this. You have to be a little careful not to divide things by 0, so that's against the rules. It's a house rule, right? So then you've got, let's just write it out again. I guess I've got 2 times both sides by 2. v0y is equal to g times t. So t is equal to 2 v0 sine theta divided by g. So that's the y component. The x component is that a sub x equals 0. So x is just equal to x0 plus v0x times t. So x is equal to 0 plus v0 cosine theta times t. And then it's the same t on both sides, so we're just going to plug that in to see how far it actually goes. So it's equal to v0 cosine theta times 2 v0 sine theta divided by g. Sorry, my handwriting is so bad there. So the v zeros come out. You get x is equal to, there's a 2. There's a v0 squared, and then there's a 2 times a sine theta times a cos theta, and then there's a divided by g. So what you do is you go over here to this trig identity, and you say that that is equal to v0 squared over g times sine of 2 times theta. So if you set maybe alpha is equal to 2 times theta, then sine of alpha is maximum when alpha is 90 degrees. So it means that x is maximum when theta is 45 degrees, I think. That's where you get that 45-degree angle in the range equation. Less than 45, and it kind of hits a little closer. Doesn't spend as much time in the air, basically, so it can't go as far. And if you launch it higher than 45 degrees, it doesn't have as much x component of the velocity, so 45 is kind of your sweet spot. And a handy little trig identity there. All right, time's in here. That's okay with that? Yep. Oh. Well, yeah, I guess if it's like a multiple choice question or something like that, you can know now that, yeah, without air resistance, if it's sort of a special case, right? If the final height is the same as the initial height, so it goes up, comes back down, and there's no air resistance, then yeah, the maximum range is 45 degrees. You don't have to rederive it. But it might ask something is slightly different or something, in which case you should probably be prepared to solve something like this. You can imagine maybe, what if the height's different or something, right? Okay, let's do another top hat question. A box of mass m is being pulled to the right at a steady speed. Okay, so, by the way, this is where I go ding, 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 ding. Constant velocity means zero acceleration, so the sum of all the forces have to be zero, right? Some of the forces in the x direction have to be zero. Some of the forces in the y direction have to be zero. Pulled by a rope that is at an angle above the horizontal. N, capital N, is the normal force on the box. So how does the normal force in this situation relate to mg, which is the magnitude of the force of gravity from the Earth on the box? Is it greater than, equal to, or less than? Or is it less than and always zero, I guess? Think about that, and if you think you know the answer, please pair up and share with your neighbor. Make sure you're both voting the same way. What you guys are thinking? So it's definitely less than mg, and as you were just mentioning, it could go to zero, actually. So D is sort of a possible answer, but it's not necessarily zero. So what goes on is it's just this. You draw a force diagram for the box. So what are the forces? Well, there's normal going up, there's mg going down, and there's tension. Okay? And there's also going to be kinetic friction. And so, and then what I can do is define my x and y axes. So I'm going to define y to be up and then x to be to the side. That way, most of these vectors, 3 out of 4 of them anyways, only have one component that's not zero. The one that does have components is the tension one. Gotta be a little careful with this one. So there's a t, if this is theta, you've got t sine theta is the tx, I think it's plus, and then the t cos theta will be the ty, and I think that's also plus. So the sum of all the forces in the x direction just equals t cos theta minus f sub k, and that equals 0, so it's going steady speed. Actually, it does nothing for us. But let's do this one. The sum of all the forces in the y direction is going to be normal plus t sine theta minus mg equals 0. And so you can solve this out for normal. Normal is equal to mg minus t sine theta. So that's less than mg, right? And in fact, if t sine theta is equal to mg, you could make normal force go to 0. And I guess if you set t sine theta more than mg, you could just lift the whole thing right off the table and set it into a projectile motion or something. Then it's no longer sliding, I guess. But there's a limit to how much you can pull this and have it slide along the table. Okay. So since we're getting philosophical, I want to go back a little bit to a table I showed you in class 8. And these are sort of the big 5 forces we use a lot in this course, Physics 131. But I want to focus on, so that gravity has a nice equation, kinetic friction has a nice equation, but these 3 in the middle are what are called as-needed forces. So what I want to discuss real quickly is how does an inanimate object like a surface know what is needed? Like how do these forces actually self-adjust in real life? Some of you were kind of asking me about this in office hours. I was thinking about this, and so what it's important to realize. And before I get to there, let's talk about springs. So there is something we're going to learn about more in chapter 7 called, I guess, Hooke's law, which is that if you have a spring, it exerts a force on whatever it's connected to on either side. And if the spring is in, I guess, equilibrium, it's its equilibrium length, then that force can be 0. But if you stretch the spring, then there's a pulling force that pulls both those objects towards each other. And if you compress the spring, then there's a pushing force that pushes those 2 objects away from each other. So, and the force turns out to be proportional to how much the spring is stretched, either longer than its equilibrium or shorter. So now we have something called Hooke's law, like a model. What we can do is model molecular bonds using Hooke's law. It turns out to be a surprisingly accurate model for small little displacements. So 2 atoms in a molecule are not at a fixed distance away from each other. They're at a variable distance. If there's a force, then they can be a little closer or a little farther. So this is how, for example, tension self-adjusts. If this person is pulling on a string and trying to move this crate or whatever, then what happens is that some of those molecular bonds between the atoms, it's as if the atoms get a little farther apart, and then by Hooke's law, the force between them on this molecular spring model causes them to be attracted to each other, and there's lots and lots of those, and that's what add up to make the tension in the string. So what it means is that really no string is infinitely rigid, right? If you pull a string, it's going to get a tiny little bit longer, I guess, because of these molecular bonds. And that is what provides the tension. Almost as if you were pulling with a spring. Okay, but it's a string. So normal force, same thing. If I were to put a big heavy textbook on a trampoline or on a pillow or something, you'd see it sort of sink down. Well, what I'm telling you is that even if you put that book on a hard surface like a table, you may not visually see it flex or sag, but it must actually do that. Even the hardest surfaces, I think, must compress a little bit when they're pushed, because that's, again, how this normal force self-adjusts. And so in this case, it's sort of opposite of tension. You've got the molecules being pushed a little closer together, so those molecular bonds are now pushing forces, and that's what, all together, as a consequence, the compressed molecular springs push upward on the book. And that's what we call the normal force. Okay? That's where it's coming from. And then the third one, I guess, this is a little harder, how static friction actually self-adjusts. Basically, when two objects are placed in contact, the high points on one surface are jammed into the low points on the other surface, or high points on the other surface. And then there's points that aren't in contact at all. So at those points of contact, there are molecular bonds that form between molecules on the two different objects. And what that means is that now if you push with a sideways force, or if there's some reason for these things to bend, you can create, these molecular bonds can create a force, if these points of contact are bent, that's now parallel to the surface. We call that static friction. It's all boiling down to these molecules. Okay. And I will post these in the post-class notes, obviously. What's next here? I think I got another top hat for you. Because this is, I think, the last section of chapter 4. They like to make the last section of these chapters something very concrete, I think. So starting, stopping a car. So a car accelerates towards the right, away from a stop sign. So its velocity is to the right, and its acceleration is to the right. So it's accelerating. There must be an unbalanced net force in the forward direction on the car. So I want you to imagine that you're drawing like a force diagram of the car or something. You want a great big force in the forward direction. So what force is that? Is it A, gravity, B, kinetic friction, C, normal force, D, static friction, or E, thrust of some kind, engine thrust or something? Maybe, I think you can really only pick one answer from this list. It's the one I like. Check your neighbor. Remember, it's 80% is just for your participation, and that extra 0.2 comes from getting it similar to me. Getting it right, I guess. But I want to convince you that I'm right here. So I've got a couple demos coming up. Survey says, so 83% of you figured out that what I'm looking for here is static friction, and D. So let's discuss this, because I don't think it's really at all obvious. So, what I'm trying to say, you would think it would be the engine, right? Because obviously, you step on the gas, away goes the car. Okay, however, the forces that the engine exerts on the other parts of the car are all internal forces. So in physics, we can't really have that. That's not going to work. Only external forces exerted by objects in an environment can cause an object to accelerate. Sort of a conservation of momentum principle right there. So what does the engine do? It rotates the wheels. And you can sort of see I've added a little arrow there on the back wheel, showing that the back wheel is kind of accelerating in a clockwise sense. So if it's rotating a little bit clockwise right now, then a couple seconds later it'll be rotating even faster clockwise. So it's got, we call it that angular acceleration. But point is, if the car was sitting perfectly still and the wheel was rotating clockwise, then I think the bottom would want to push backwards on the road. It would want to slip backwards on the road. But it doesn't slip because of friction. which pushes it in the opposite direction it wants to slip, which is to the right. So the force that's responsible for this forward push is the static friction. And we call it FSG on W, so the static friction force of the ground on the wheel. That's the big forward force on your force diagram of the car, which causes it to accelerate in the forward direction. And this was question 3. Friction force is acting in the same direction, actually, as the car as it's moving, which is a bit weird. So, question: why is it static friction and not kinetic? Well, no matter what the speed, 4 points of this car are always at rest. Which points? The bottoms of the 4 tires. This is known as rolling without slipping. And like I was saying, if you saw those construction guys outside, they had these continuous tracks. You can imagine with this, that with a continuous track, as it's rolling along, it's kind of laying down tread, and it kind of goes over it. And you can even imagine maybe spikes on the bottom of the tread that are like poking into the dirt. Well, they're not slipping, right? They're just static as the whole thing rolls over top of it. Can we try the video? What do I push? Aux plate? I don't know if you can believe it. Doesn't seem to want to. Just looks black. Is it gone on screensaver or something? I sort of want to show it with an actual wheel. Okay, we got a couple of these wireless HDMIs are the best. There it is. So as this wheel goes along, what I've kind of done is I've maybe this piece of tape. Imagine it's rolling along. Well, for an instant, this tape is laid down, and then it's pulled back up off the back. And that's true for the bottom of the tire at any moment of time. Another way of looking at it is that if this is spinning along so that the outside is moving at some speed, and I move the axle at that same speed, so the bottom is going to the right relative to the axle. If the axle is going to the the bottom is going to the left relative to the axle. If the axle is moving to the right with that same speed, then relative to the ground, the bottom point will be at rest, just for a moment. And so it's almost exactly like the continuous tread on that construction equipment, right? It's being laid down, and then it's being pulled back up. And I guess you can imagine if it wasn't rolling, it would kind of slide along, and that would be like kinetic friction. But if it's rolling, then it's static friction. So that's awesome. I also have let's see here, okay. So let's look at some comments from this morning. Okay, this was actually from one of you. One of the thinking is that as the car accelerates, the tire exerts a greater and greater force on the road in the opposite direction of the car's movement, assuming the car is moving forward in the positive x direction. Then static friction in turn exerts on the force same magnitude as the car's tires in the direction of movement of the car, according to Newton's third law. So that's exactly it. And then can you explain what skidding is? So skidding would be when the two surfaces are moving relative to each other. And that's kinetic friction, also called sliding or slipping or skidding. I think all those words mean the same thing. And what happens too is that if you have a car that's doing it, it makes this sound, screech, like that. And you'll know. So unless you're hearing that sound, it's never kinetic friction. And actually, kinetic friction has an equation for it. It's just mu sub k times the normal force, and it's always in opposite direction of the velocity. So the magnitude is set, and the direction is set. So if you've locked all your four wheels and you're screeching along the ground, you are not able to steer because it's always just opposite the velocity. It's going to slow you down. So if the road turns or something like that, and you're screeching all four of your tires, you're going to go straight in the ditch. So it's generally a bad thing to be skidding. So here's a little PowerPoint animation. You can imagine a triangle rotating around the bottom pivot, right? So the pivot's not moving. You believe me? Let's watch it again. It's just sitting there, right? So now imagine a square. Now it has 4 sides. If I turn that, well, again, that point in the bottom, not moving. It's at rest. See where I'm going with this? If it's this octagon, 8 sides now, bottom part is not moving. Okay, et cetera, et cetera. If you have an infinite number of sides, like a circle, the bottom would not be moving. And then this is a video of a marble. So what we're going to do is, first, like I can show you, so Jonathan, I think he took his iPhone and did a slow motion video of just tilting the table and the marble rolls along. That's rolling without slipping. But what if you took away the friction? So this is a pan of ice. You just stuck that in your freezer and made an ice tray. Okay. I should let Jonathan do this one. And then he took the marble, and again, it all happens a bit fast, so he put the slow motion thing on his iPhone, and we can, not that one. Did that one already? Let's do this one. Look at that. That's the marble not even rotating at all. Clunk. A little delayed reaction there. So why does it roll? It rolls because of the static friction. That's what spins it and causes it to turn around. So there's something, I guess, you could do slipping without rolling. So that's going to be really important in this next top hat question. I'm going to do 2 questions about a car that has front-wheel drive, meaning that the engine is only attached, really, to the front wheels. So when you go vroom like that, if you imagine that you were like in ice or something like that, then I guess the front tires would spin around, right, because they're connected. But the back wheels are what are called just free wheels. They're just connected to a low-friction axle, and they kind of drag like a wagon. So what's the question? You're sitting in your car, you step on the gas pedal, the car accelerates forward, and your car has front-wheel drive. This means the front 2 wheels are connected to the engine, but the back 2 wheels are just freely rotate on their axles. As you accelerate, what is the direction of the force of static friction of the road on the front wheels? And then I'll ask a question about the back wheels. So think about that, and check your neighbor. Vote in. This one I'm only going to give you a minute on. This is a quick little quiz, because it's meant to be kind of easy. We just talked about it. You click in a direction here. Okay, 10 seconds. Please click in. And then I'll talk about the rear wheels. You got it. Okay. So basically, that's what's making the whole car go, right? They want to slide backwards because they're rotating clockwise, so that pushes you forward. Next question is, same exact question. As you accelerate, what is the direction of the force of static friction of the road upon the rear wheels? You want to think about why are the rear wheels rotating at all? They are rotating they're rolling without slipping. Sort of like the first marble you saw in the video. Okay. Let's finish up, and then I'll discuss why I think it is. So it's 50-50. I like B, and I'll show you why. So, first of all, the whole car is accelerating towards the right. Okay. Wait, sorry, this is wrong. This one. It's the fifth question. So, what I would say is that this axle is connected to the car. Connected to the car. So it's getting kind of dragged along, as if you were pulling a wagon, okay? And I guess the front wheel is where all the external force is coming from, but the whole rest of the car is getting dragged along. So then the question is, does the back wheel rotate? Well, yeah, it does. Just like the wheels on a wagon, it rotates. That's what it's supposed to do. Same as, like I was saying, that marble you rolled on the table, it rolled because it was rolling without slipping. The rear wheels here do rotate. So the question is, why the heck would they rotate? Because they're not connected to anything. As the car, not only do they rotate, but their angular velocity is increasing, I guess, as the car is speeding up. So as the car accelerates, yeah. So why? I think that this is due to a small, I didn't see how big it is, backward static friction force. It's obviously not as big as the forward static friction force on the front wheels, because otherwise it wouldn't accelerate at all. But it's got to be there, I think. It's just enough to spin a wheel. Okay, so when you had the marble that was rolling, was, I guess, slipping without rolling on the ice sheet, it was going along like this. But if it's not an ice sheet, then that static friction force is going to push backwards, I think, on the wheel because it wants to slip forward. And that's what's going to spin it up, actually. You believe me? It's a tricky one. I like to keep you guys on your toes with this stuff. Let me just, so I don't have time for the example. We'll do the example next time. But here's a tire moving to the right at constant speed. In this case, you've got, I guess, no static friction. But if you've got the tire moving to the right and it's turning faster and faster, then you've got a forward static friction on the road. So if you've got this like engine that's causing it to turn faster and faster, this is like, I would call this the, I guess, engine torque. Then static friction speeds it up. You could also have a brakes torque. You put on the brakes, and then some brake pads push into each other, so that now you've got a counterclockwise torque slowing down that thing. Now you're going to have a static friction again from the road backwards on your car, which will slow down your car without screeching. And then I think what I'm going to do next time is I'll do in principle, what's the shortest possible amount of time you can accelerate from 0 to 100 kilometers an hour, and I'm going to use that mu sub s of rubber on concrete is 1.0. But meantime, you can start in on chapter 5, and this is actually a question from one of you. Is a car traveling on a circular track at a constant speed, is it accelerating or not? I'll see you on Friday.